Okay, today we're going to go deeper into finding volumes. And so we want to make sure we know our general formula for finding the volume of a 3D object. And I hope we all remember that it's just the integral from A to B of the areas along the way. So just like areas are the integral of the heights, so area is the integral of heights at each x. Volume is the integral of the areas at each x that are, perpendicular to the x-axis, if we're going perpendicular to the x-axis. Now, here we have the graph of y equals sine of x squared plus 2 on the interval from 0 to 3. This is 100% a calculator question. You can do antiderivatives. You can find volumes without a calculator by doing antiderivatives, but let's consider why we can we not do the antiderivative of sine of x squared? Well, it looks like it could be a u substitution, but the derivative of the inside would be 2x if that was u. If x squared was u, then du would be 2x, and there's no x on the outside being multiplied, and so it's not the result of a u substitution, and in fact, we can't do this using any techniques in this course. So this isn't something you can find you can find the antiderivative of 2. The antiderivative of 2 is 2x, but you can't find the antiderivative of this because you can't do the u substitution because you don't have the derivative of the inside multiplying on the outside. So you need a calculator, and our first few questions are questions that you should be able to do from our previous classes. Let's start with finding the area of the shaded region. What is the area of this shaded region? And hopefully you started by putting y equals sine of x squared plus 2 into your calculator. We know the window is going from 0 to 3, so I usually set mine to go from like -1 to 4, so a little bit before it till a little bit after. I can see that I usually just go with whatever's in the graph. So the y min is -1 and the y max is 4. So y min is -1 and the y max is 4. And then you can get a really nice picture of what's going on there. And what we're doing is we're going to be doing the integral. You can actually do it in here too. You can do the integral. But, oh man, I didn't mean to go there. I don't know what I just did. Okay, whatever. The integral from 0 to 3. You can also do it in the graph section, or you can do it on the main screen, either way. But it's the integral from 0 to 3 of this function, and the bottom function is just 0, so you don't need to say -0. So it's just the integral from 0 to 3, and you want to have this written down of sine of x squared plus 2 dx equals, we need to go to 3 decimal places, 6.774. The AP exam would also give you credit for 6.773. Okay, so hopefully we're feeling good about this. I'd also like to point out it's really useful if they call it y equals, and we're going to be using it in multiple places, to write on your paper. On the free response section, you need to write this on your paper to be able to do this technique. But if you say f of x equals, and then you write what the thing is, then you can always, instead of writing it each time, you can just use f of x. So this is the integral from 0 to 3 of f of x dx. Now, if you didn't write this, then they wouldn't know what you were talking about when you were putting f of x, right? And so you couldn't use it. But it's a nice trick to, like, if they put y equals, just say f of x equals, and now you can call it f of x for the rest of the time. Okay, another one you should already be able to do. This area is the base of a solid. So there's a 3D figure that is sticking out of the page. For this solid, each cross-section perpendicular to the x-axis, so each cross-section perpendicular to the x-axis is a square. So there are squares sticking up out of the page. Hopefully you can envision that. What is the volume of this solid? Okay, well, hopefully you recognize what you needed to do from last class. It's still the integral from 0 to 3, and we need a formula for the area of each x. And the area at each x is going to equal, the area of a square is the length squared, and we can find this length because this length is just this height, whatever this height is. And the height at each x will be given by this f of x. Now, I wrote f of x up here. So the area is f of x squared, okay? And this is actually completely like, if I put a of x equals this, integral from 0 to 3 of a of x, and I've defined f of x somewhere, this will get you full credit on the AP exam because I've linked everything. But more commonly what people would write is the integral from 0 to 3 of sine of x squared plus 2 squared. You do need to make sure that this whole thing is being squared if you do it this way, right? And so let's do it. Let's put math 9, so integral from 0 to 3 of, and guys, I'm just going to use my y variable. Once I've typed it in once, it's so much easier to just do this than type it in again. It makes the chances that you make mistakes way lower. So this is 16.405. Again, we round to 3 decimal places. And again, I'm gonna pitch, once you've already put it in y equals, you know, putting y1 squared by going to the y variables is a lot faster than, you know, typing this whole thing out again. Okay, this area represents the base of a solid, but now each cross-section perpendicular to the solid is semicircles. So there's semicircles sticking out of the page. And that's gonna go along this base of a solid. What's the volume of that solid? And hopefully you, again, realize it's integral from 0 to 3 of a of x, but now the area at each x is going to be, the area of a semicircle is 1/2 pi r squared, and the radius, oh, you guys can't see this, oh no, that was off the screen. Here's a semicircle sticking out. The radius of this semicircle is half of this height. So the radius is f of x divided by 2, right? And this actually, right here, gets you full credit for having written it down. Because we said what f of x was up here. The radius is f of x over 2, and this is great. But I mean, more commonly people will write the integral from 0 to 3 of 1/2 pi times, now we gotta be careful here. R is this function, so sine of x squared plus 2 divided by 2, right? Squared. So 1/2 pi r squared. And we talked about before how this always simplifies, where if the semicircle ones, when you square it, the 1/2 squared, a half times a half is a fourth, and that'll multiply over here to make 1/8, and the pi can go on top. So a lot of people will write pi over 8 times sine of x squared plus 2 squared, like this. Like this is also fine. But check it out, guys. Like if you factor out that pi over 8, then I can just use the same one as before times pi over 8, and I don't even need to like redo the integral. Otherwise, like it gets a little bit ugly. I have to press math 9 integral from 0 to 3 of 1/2 pi, and then I need to put the r in parentheses, sine of x squared plus 2 squared. Put plus 22. Oh, and then this needed to be divided by 2, or I need to have a 1/2 in the, but then the sine of x all needs to be multiplied by 1/2. It becomes really tricky to get the parentheses right, to get it right. Like this will come out right, but it's hard. Oh man, maybe it won't come out. Oh, I didn't put dx. This will come out the same, I think. I think I typed it in right, but you can see how easy it is to mess this up. Whereas, you know, if I do math 9, 0 to 3 of 1/2 pi, and the r is going to be 1/2 variables y1 squared. Like this is a lot easier to type in if I start using the y1, right? It'll also come out the same. But I hope we can see how using that y1 can really simplify things. And, you know, if you know the trick that semicircles, it's always going to be a pi over 8 times just that diameter squared. That's nice. Okay, so this came out to be 6.442. Okay, this area is the base of a solid. Now each cross-section is a rectangle. And the height of the rectangle is going to be 6 more than the base. Be careful, be very careful here. 6 more than the base, not 6 times more than the base. So the height is going to be taller than the base is. So here are these rectangles sticking out, and the height is 6 more than the base. All right, so what's the volume of that solid? And hopefully we recognize that this is the integral from 0 to 3 of f of x. That's this height is going to be f of x, and I've already written it up there, times the height is going to be 6 more than the base. So whatever this was, this one is 6 more, and that is f of x plus 6. That is the height of the rectangle. So this is the length times the width of the rectangle. The length is f of x right here, and the width or height or whatever you want to call this is f of x plus 6, because it's 6 more than the base. And so I'm just going to do this in a calculator. So math 9, integral from 0 to 3 of y1 times, I'm going to type in y1 plus 6. And that y1 plus 6 needs to be in parentheses so that it actually, distributes. I also could have, for y1, instead of doing it, I could have typed out sine of x squared plus 2, but again, it's going to get really ugly with the parentheses to make sure it's right. So this is 57.046, okay? Let's see. This is the last one you should already be able to do. The area represents the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a rectangle whose base lies in the shaded region. So we've got rectangle again, whose base lies in the shaded region. But the height of the rectangle is 6 minus x. So, okay, so this is 6 minus x. Okay, so hopefully you can find the volume of this solid. So the volume is going to be the integral from 0 to 3 of the length times the width. That's the area of the rectangle. And the length is f of x. And I could, of course, write sine of x squared plus 2 there if I wanted, times, it would need to be in parentheses though if I did that, times the width. It said the height of each rectangle is just 6 minus x. That's it. So it's this, which is f of x, that's the base of the rectangle, and then times 6 minus x, which is what they told us the width was. So let's see. I'm just going to, oh man, I can just like go up here and do 6. I'm going to change this to 6 minus x. So y1 times 6 minus x, that'll give me the right answer. So it's 30.686. Or, of course, I could have typed in sine of x squared plus 2 here into my calculator, but it just makes it so much less likely that I make a mistake if I use the y variables. Okay, now, here is a new thing. And I'm going to actually switch over to a blank paper just so I have a clean paper for what's going on here. What if we find the volume of the solid created when this shape is revolved around the x-axis? So here is the x-axis. And they're going to take this shape. Boy, I actually want to, ever since last year, I don't actually know where some of my stuff is. Like, I don't know where my scissors are. Guys, excuse me for just a second. Go do something for a minute and find some scissors. Okay, so what I'm going to do is I'm going to cut out a shape that's kind of like this guy. I don't need it to be perfect. Like, I don't actually care if it's exactly like it. It kind of goes up, and it comes back down, and then it goes up again, and it kind of comes down, whatever. This is kind of what it looks like. So, whatever. Here's our shape of this graph-ish, okay? And what we're going to do is we're going to take, oh man, I'm going to raise this higher. I hope this will work. Okay, we're going to take this and we're going to revolve it. To revolve it means to like spin it around. And what we're going to look at is like, imagine that this is like a solid sheet of metal and it's cutting out space as it revolves. It's making a shape. So as we revolve this, it's cutting out a shape in like clay. Man, this would be so much easier in a classroom than on a video. So we're revolving it, and it's cutting out a shape. I want you to imagine to yourself, as this shape revolves around the x-axis, what's that shape going to look like? What 3D figure is going to be created as it cuts out space along the way? And hopefully you can see it kind of looks like a vase, you know, like a vase where it's like going up and around. And what's going to happen is if we take, remember, our general formula is the integral of the area at each x. So as this revolves around, at each cross section, it's going to make a circle. And, you know, the circle, like as this revolves around, at each like spot, it's going to cut out space that's equal to whatever this height is. This will be the radius of the circle that it's cutting out along the way. Like as you spin it around, you know, this radius is cutting out space if we were to slice it. And it's going to make a circle. This is the center of rotation. You always want to pay attention to what is the center or the axis of rotation. This is the axis of rotation. And this radius will be from the axis of rotation till the end of this, and it will make a circle. And what is the area of a circle? Well, the area of a circle is, in this case, pi r squared. So the area at each x of a circle is pi r squared. And the question, let me put this back down, you guys can't see. Oh no, my dock cam fell over. Too heavy. It's off balance. Okay. And now, yeah, here we go. Okay, so the area of a circle is pi r squared, and the question just becomes, what is the radius? And the radius of this circle, this is always what we're going to be thinking of, is it's going from the center of the rotation to the outside edge of the thing that's cutting out space as you revolve it around. That will be the radius. And so this radius, this height, is f of x, as I defined earlier, y equals x squared plus 2. So the area at each x will be pi times sine of x squared plus 2 squared, the radius squared. Again, it makes you way less likely to make a mistake if you've defined f of x somewhere and you're just like, oh, pi f of x squared. And so the volume is going to be the integral from 0 to 3 of pi times f of x squared. And pi is a constant, so sometimes we'll bring it to the outside if you want. Integral of pi times f of x squared from 0 to 3. And we've already calculated the integral from 0 to 3 of f of x squared, but I'll take this in again. So math 9, 0 to 3 of pi. Again, guys, this y1, y variables, y1 squared is the way to go. It's just like looks so clean, right? It's just like isn't complicated. Whereas if you're typing out the whole sine of x squared plus 2 squared, it's easy to make a mistake when you're typing it in the calculator. I keep harping on this because like the number one mistake that people make on these things isn't like understanding it. Well, I mean, at first people have a hard time understanding it because it's new. But after a little while, calculator errors become like the biggest source of errors. Okay, what if we create a solid by revolving it around the line y equals -1? So I'm gonna do it in red here. Here's the line y equals -1, and this is going to be our center of rotation. So you can kind of think of it as like, okay, there's this blank space in between, and it's revolving around, and it's making a blank space. And what it'll look like when you revolve it is, again, as you revolve, it always makes circles, but what it's going to do is it's going to have like this blank space. Here, it's going to have like a blank circle and a filled in circle. And the whole shape is going to be like a vase with like a hollow center. It's actually going to have like a center that's hollow because the only thing that's cutting out space is this shaded part, not this blank part. So when it's revolving around y equals -1, there is a space between the axis of rotation and where the area starts. And when that happens, what it creates, the shape it creates, is a disk. So this is called a disk or a washer, sometimes we'll call it. And the way we find the area of a washer is we think of there being two radiuses. So we think of there being like a radius from the center of the circle to the very furthest part where it's shaded the furthest part away. So that's this distance, okay? And we call that the big radius sometimes. And then the very center of the circle to where it stops being blank, we'll call that the little radius, okay? And that's right here. So in the way you find it is you calculate the big circle, the area of the big circle, so pi times big R squared minus pi times little r squared. So what that does is it finds the area of the whole circle, and then it takes away the blank part, which is the area of the little circle, and it gives you the area of this like donut-y looking shape. And so that's what we're going to do here. Whenever the axis of rotation is not on the edge of the area, but further away from it, we'll need to start with the center of rotation and find this distance. Now, a vertical distance is always just like the top y value minus the bottom y value. So the top y value is f of x, and the bottom y value is -1. And so I'm going to write down here, this is going to be the integral from 0 to 3 of pi times big R squared minus pi times little r squared. And over here, I'm going to define what big R is. Big R is the radius from the axis of rotation to the edge of the shaded region. And it's always going to be the top y minus the bottom y. So here the top y is f of x and the bottom y is -1. And so it's going to be f of x minus -1, which simplifies. Minus -1 is +1. And that should make sense, right? The distance at each x is going to be f of x, whatever this f of x is, plus 1, because the distance here is 1. And so the big radius is going to be 1 plus f of x. So that should make sense from that perspective. And the little radius is going to be from I guess I'll do this in red. The little radius is axis of rotation to the edge of the blank section. So in this case, it's the axis of rotation to the edge of the blank section. And we can see that this distance is 1, but sometimes it's a little bit harder to see. It's always, again, going to be the top y minus the bottom y. And here, the top y value is 0, and the bottom y value is -1. And so 0 minus -1 is +1, which is this distance. You can see that the distance of the blank section will always be 1 in this case. It won't always be like this. So little radius is 1, and this is fine. This like gets us full credit. But if we were to type it into a calculator for like writing it out, this would give you full credit because we've defined what big R is and what little r is. Sometimes you'll see this written, you can factor out a common factor of pi. A lot of people like to write it like this, pi times the integral, because then the pi will distribute to both. So from 0 to 3 of, and then it'll just be, so another way to write this, I'm going to write it right here, is pi times the integral of big R squared minus little r squared. That's another way to do it. So y variables, and the big radius was y1 plus 1. That needed to be in parentheses being squared. Hold on. So the big radius squared minus the little radius squared. The little radius was 1. So the big radius is f of x plus 1, or minus -1, whatever. The little radius is that. So hopefully we feel okay about this so far. Why don't you guys try doing, you do this last one, and it's going to be a little bit different, but see how you can do. Find the volume of the solid created when the shaded area is revolved around the line y equals 4. So now this is the axis of rotation, and you're revolving this shaded area around this line. So try it on your own. You might not get it right. This is tricky for a little while until you get used to this. So this is now the axis of rotation. This is where the center of the circle is going to be. And the radius, the big radius, is going to go down to here. And it's going to spin around and you'll see there'll be like a blank spot because the shaded region will go around. Man, I wish we were in person. This is so hard to do over a camera. And the little radius will be this distance, right? The blank, from the center of the circle to where the blank part ends. So the big radius is always from the axis of rotation till where the shaded area ends, and the little radius is always from the blank part in the middle of the circle. Again, it's making a little radius here that's going to be cut out in the middle, and so the little radius is where the blank part ends. So what are those distances? Well, in this case, the big radius, again, it's always top y minus bottom y. The top y here is 4. So this is going to look different, right? The big radius is going to be the top y, which is 4. In this case, the top y value is 4, minus the bottom y value, which is 0. So the big radius will always be 4. And that makes sense, right? Like, okay, from here to here, no matter where you are, is always going to be 4. From y equals 4 to y equals 0 is 4. And the little radius is going to be this top y until the edge of the shaded part. And it's always top y minus bottom y. So the top y is 4. The little radius is 4 minus the height as you're going along at different x's is f of x. So 4 minus f of x. That's the little radius. And so this is pi times the integral of 4 squared minus f of x squared dx. And that is our answer. Oh, wait, no, hold on. Sorry, 4 squared minus 4 minus, oh, this is so ugly, guys. Scratch that, reverse it. Pi times the integral from 0 to 3 of big radius squared minus the little radius we said was 4 minus f of x squared dx. And that looks quite different than, this other one where the big radius was f of x plus 1 and the little radius was 1. This looks quite different. But if you just think about like what's the center of rotation, then it usually goes very well. And so let's just calculate this. So integral of, let's see. I guess I should have just started over. This is not going to save me any time. Of 4 squared minus 4 minus, really use the variables, guys. It's going to make it go much easier. y1 squared dx. And that area is 118.701. We always go to 3 decimal places. So, guys, if you got that right on your own, good for you. I'm very impressed. It's the kind of thing that almost everybody struggles with the first time they see it. All right, let's go on to the back, and you'll get another chance to practice this before you get to your homework. So here's f and g. F is 1/4 sine of pi x, and g is 4 to the negative x. So I guess this is, it tells me it labels them. That's nice. Sometimes it labels it, sometimes it doesn't. R is the shaded region here, S is the shaded region there. Find the volume if S is revolved around the x-axis. So here's the x-axis, this is the axis of rotation, and S is being revolved around it. Hopefully we can see there's a blank spot here, but go ahead and try this on your own. What is the volume? And hopefully we can see this is the axis of rotation. And so we go kind of to the far edge. This is like the circle it's going to be making. And the big radius is always from the axis of rotation to the edge of the function, right, to the edge of the shaded region. So big R is going to be just f of x. That's nice. And it's got it labeled for us here that this is f of x. And the little r is going to be the little radius, the blank radius, is from the center of the axis of rotation until you get to the edge of the blank. And that is g of x. And so this is pi times the integral of big radius squared minus little radius squared. This is all you need to type in because f of x, write down because f of x and g of x are clearly defined in the problem, and so the AP exam will know exactly what you're talking about there. In your calculator, you need to put in, we need to find what the limits go from. So let's go ahead and do that. So we're going to put in 1/4 plus sine of pi x, and y2 will be 4 to the negative x, and let's make my window go from -1 to 4. Yeah, that looks fine. We should be able to see this nicely. It's going too far. Okay, let's go from -1 to 1.5. Is that good? Yeah, that way we can see it more clearly, like this is the area we're talking about. And honestly, we should probably go from like -0.5. Now I can see this graph pretty well, like what's going on here. Okay, so I need to find the intersections. And one of the intersections, this integral is going to start at 0.178. And the other intersection, enter, I need to press over to the right before I press my guess. So once it's on this guess, we need to put it so it's closer to the one on the right, and then press enter again. And that intersection is x equals 1. So that's nice. Okay, so the intersection here is going to be there. So we're going to press math 9, intersection from 0.178 to 1 of, oh, I forgot to factor out the pi. Let's put the pi on the outside. F of x was y1 squared minus y2 squared. This doesn't usually come out like this, but sometimes it does. And here we go. 1.98. 1.980. You can actually write this as 1.98 and get full credit. You don't need to write 3 decimal places if the last one is a 0. So hopefully you're feeling okay about that.